Hi, I am Carla Vargas Mauredo. I graduated in the pharmaceutical biochemist career from the University of Campeche. I am here to talk to you about in my grad thesis project, synthesis of silver nanoparticle from expired ibuprofen waste for removal of malachite green contaminant. Let's talk about the ibuprofen. It belongs to the family of non-steroidal anti-inflammatory drugs, NSAIDs. This family shares antipyretic, anti-inflammatory, and analgesic activities through its ability to inhibit the production of prostaglandins. The high consumption of ibuprofen increased during the COVID-19 pandemic. This anti-inflammatory is considered a first-choice medication due to its low probability of causing gastric irritation and is available over the counter in Mexico.
On the other hand, the over-the-counter availability of medication influences self-medication. Other factors, such as change in the prescribed practice, can lead to the presence of expired and surplus medication in households. Greater ease of access to medication will increase the risk of improper disposal, as pharmaceutical waste is often discarded alongside regular trash, toilets, or sinks, a common practice in Mexico. Consequently, this substance can affect aquatic organisms by altering their production, development, and behavior, in addition to causing harmful effects on human health and environment.
In general, medication collection programs aim to reduce environmental pollution by providing a relative safe disposal of expired medication at the time of collection from the public. However, the critical failure of these programs is throwing the collection medication into the incinerator, which allows pharmaceuticals to enter the environment, therefore reducing or postponing their destructive entry into the environment and avoiding a double economic loss is an urgent priority. The lack of innovation to improve proper medication disposal methods is a significant change. On the other hand, dyes contribute to the pollution of marine ecosystems. Most of these dyes are difficult to decolorize due to the complex chemical structure. Thus, malachite green is not considered a typical organic contaminant, which offers opportunity of nanotechnology to play a significant role due to its properties. Malachite green is used to color a wide range of materials such as textiles. It also has various applications in aquaculture due to its antifunctional and antiprotozoal properties in fish. In Mexico, this practice is whispered due to a low cost, high efficiency, and great availability, along with a lack of alternatives.
To produce silver nanoparticles, silver nitrate was used as a precursor, with ibuprofen serving as the reducing and stabilizing agent, while sodium hydroxide acted as an accelerator for this reaction. To carry out the synthesis, inferred extra ibuprofen from an expired commercial tablet using methanol. Then, the three synthesis methods were proposed and differ in the order of reactants. In the first method, all reactants are combined following by heating to 100 degrees Celsius for a synthesis time of 10 minutes. The same time and temperature are maintained for all syntheses. In second method, silver nitrate and sodium hydroxide are added at room temperature, and then the temperature is decreased before adding ibuprofen. In the third method, silver nitrate is added at room temperature, and Then the temperature decreased before adding ibuprofen and sodium hydroxide.
After determining the best synthesis method, certain parameters were varied, such as the time at 10, 30, and 60 minutes of synthesis. Once the optimal time was identified, the synthesis temperature was varied to 70, 80, 19, and 100 degrees Celsius. The best variation was selected and the concentration of ibuprofen was varied to 250, 500, and 1000 microliters of ibuprofen at 0.5%. All of this aimed to increase the production of and improve the producibility of silver nanoparticles. Then the point of the nanoparticles to eliminate the malachite green contaminant under direct sunlight was evaluated. Let's talk about the results obtained. Figure 1 shows the monitoring of silver nanoparticles over 50 weeks, which allowed me to observe that these nanoparticles increase their absorbance over time, such that after week 7 there is no further change in the absorbance. However, in Figure B, we can see the methods 1 and 2 show high variability in the results, while the method 3, although in the produce lower absorbance, yields more reproducibility results compared to the other methods. Reproducibility is an important parameter for controlling the synthesis and therefore for the application of silver nanoparticles. Once we obtain the best method, method 3, I decide to vary the temperature at time to increase absorbance, which is relative to the production of silver nanoparticles. In Figure A, the synthesis at a low temperatures, 70 and 18 degrees Celsius, yields significant absorbance, indicating low production of nanoparticles. However, when the temperatures are greater than or equal to 19 degrees Celsius, an increase in absorbance is observed, which is associated with an increase in the production of nanoparticles. As for in Figure B, an increase over time leads to an increase in the absorbance of nanoparticle production. A synthesis time of 16 minutes results in lower variability and in decrease the production compared to the 10-minute synthesis. Finally, in Figure C, the volume of ibuprofen was varied for the synthesis in decrease the superfluous plasmon and the production of nanoparticles, as can be seen at 1000 microliters of ibuprofen. Plasmon resonance of 1.4 is obtained along with significant dispersion, unlike the synthesis with 250 microliters. From this, we can conclude that the ideal methodology is a method 3 at 60 minutes and 100 degrees Celsius. The volume of ibuprofen will depend on the application of the nanoparticles.
The identification of the nanoparticles was done using a scanning electron microscope at the center where I conduct my research. In image A corresponding to the synthesis with 250 microliters of ibuprofen. Other morphologies in the shape of bars, triangles, and small spheres can be observed at a resolution of 20,000 kilovolts. In image B, corresponding to the synthesis with 1,000 microliters of ibuprofen, spherical points can be seen in the distance. The microscopic resolution is not sufficient to observe the actual size of the nanoparticles, but we can estimate that there is greater polydispersity in the synthesis with 250 microliters of ibuprofen compared to that of 1000 microliters. Image C corresponds to a synthesis of ibuprofen with nitrate without solvent, which was heat and analyzed. Under the microscope were observed a morphology, resembling flakes and upon performing EDS analysis. It corresponds to silver and chlorine. This indicates that ibuprofen reduced silver nitrate to produce metallic silver.
Next, we have some infrared spectra where in figure A corresponds to expired ibuprofen in powder form, and we observe the characteristic peak at 1700 centimeters minus 1, which corresponds to the carbon-oxygen double bond of the carbonyl group. In figure B, we see a spectrum of silver nanoparticles, and the same bond of the carbonyl group appears but shifts to 1635 centimeters minus 1. The identification of carboxyl group is often difficult due to the overlap of binding and stretching modes and the strong degree of hydrogen bond with solvent molecules and viral nation coupled with carbon-carbon and carbon OH. Now, let's talk a little bit about the application of these nanoparticles. A stock solution was prepared at a concentration of 3 times 10 to the minus 4 molar, and from this solution a 100 dilution was prepared. The exposure solution consisted of the 3 milliliters of silver nanoparticles combined with 3 milliliters of malachite green dilution. And the malachite green blend plus water also corresponds to the same volume. This solution were exposed to the sunlight of 50 minutes and then analyzed using UVBs in range of 240 to 800 nanometers. In the first spectrum, 2 peaks are observed. One, around 410 nanometers, corresponds to the nanoparticles, and other at 619 nanometers corresponds to malachite green, whereas in decrease in the absorbance of malachite green is nothing. On the other hand, the blend remains unchanged. The percentage of degradation of malachite green was calculated to be 72%. The elimination of malachite green may be seen when sunlight irradiates to the surface of the nanoparticles. The electrons in the valence band of the metals are excited to the conduction band, generating positive holes in the valence band, which can be reacted with water and produce hydroxyl radicals. The electron in the conduction band of the metals react with oxygen molecules and reduce them superoxide anion radicals. These radicals are highly reactive and cause the degradation of the dye. Finally, we conclude the expired ibuprofen produced silver nanoparticles with a surface plasmon of 410 nanometers. The 3 synthesis method, which use a synthesis time of 60 minutes and synthesis temperature of 100 Celsius degrees, obtain the best synthesis reciprocity of silver nanoparticles and the highest superplasmon intensity. This nanomaterial has the capacity to eliminate the organic contaminant malachite green. Thank you for attention. I hope this can be of interest to you.